Hang on. It's the wrong one. All right, I think I sent everybody their quiz. Hopefully y'all got it back. And hold on for 1 second. All right, I'm just going to go through this. The first problem was at 100 megahertz and the power was 20 watts per meter squared. Well, I know that, oh, come on. I know that average power is equal to 1/2 magnitude of E squared divided by, I don't know why it does that, divided by eta. So from there, I can calculate E by just taking 2 eta times P av and taking the square root of that. That's simply the magnitude. That was 122.8. And then to get the, because it's an air, to get the magnitude of the H field, it's just E over eta. This is a simple box checker. These are things that should just be pretty much automatic from the last part of EMAG 1 to the first part of EMAG 2 from the equations and what we've discussed. The next part I want to talk to you about and make sure you understand this. This is the part that concerned me. When we have a field equation as such here, the first thing that you have to do, can you all see this, by the way? I've got to make sure. You see my sharing screen? You see it's highlighted?
We can.
When you look at this, AX is not the direction of propagation, but AX is the polarization. It means the E field is oriented in the X direction. The vector direction of propagation comes from the coefficient of the exponential e to the j 40z. Z tells you it's in the z direction, but the plus j tells you it's in the negative z direction. Does everybody follow me on that? All right, that's how you always get the direction. So AP here would be minus AZ. Now I know that I could get H in a couple of ways. H can be defined as 1 over eta AP crossed into the E field. That's one way to get it. Does everybody understand what I'm talking about there? All right. It can be defined in terms of those equations in your book, or I know just from common sense that E crossed H is the direction of propagation. Well, E is in the X direction. It's propagating in the minus Z direction. So H would have to have a negative sense to it. Do y'all follow me? I can do it that way as well. I know it'll have a negative sense. In this case, the magnitude of H, since it's in free space, is just going to be 20 over eta, where eta is 120 pi. And it has the same form of the exponential in terms of its propagation in phase. And the unit vector AY tells you it is aligned on the y-axis. Now I can get this, and I'm going to put this out here for everybody. Let me do it right here. I know that if I want H, I can get it. I can get H equal to really 1 over eta. And then it's going to be A sub P crossed in. Oh, come on, isn't that it? Times in the E field. Now that will give it to me too. All right, do y'all remember that from your book? And you had, this is open book, so these equations are right in front of you. So you just have to know how to execute them. Make sure you do this because this is not in any way, shape, or form difficult. This was sort of automatic. And the way you get frequency is look here. There is no minus alpha. And if it says in free space, it means there's no attenuation. So beta right here, and I'm going to put this right here for everybody to see. When I take a look at gamma, sorry about that. Gamma is equal to alpha, right, plus j and then times beta, right? And that's equal to the square root of j omega, oops, sorry. Square root of j omega mu times sigma plus j omega and then epsilon. Now, this is the point I want to make. If it's lossless, sigma is 0, right? And if sigma is 0, then this thing is just going to be j omega, right, times the square root q. Square root of, and there it would be simply, if you look at this, mu times epsilon. Well, that's equal to what? That's equal to j omega, right? But the square root of mu epsilon in free space is really 1 over the speed of light, isn't it? It's just divided by c. You follow me on this, class? I'm saying if it's lossless, then this is true. So since we know it's lossless, there's no alpha, it says free space. Therefore, omega over c is equal to 45, or I could say that omega is c times 45, c times beta, and therefore f would be c times beta divided by 2 pi. Do you all agree with me? So that's just checking boxes to make sure you understand how to do these things quickly. That was the first one. The second one, again, the propagation vector, there we go to this point right here to look for both the direction and the orientation of propagation. It's in the y direction, but it's in the plus y direction, right? Y'all follow me on this, class? That's the H field. To get the E field, I can do it a couple different ways. I can take E cross H is the direction of propagation, or I could get the E field, and I'll put this here just for everybody's sake. And y'all are gonna, what I'll do is take a shot of this, and I'll send you this. How's that? I'll just email this thing to you. That way you'll have it in front of you. Right here, I know that the E field itself, E is equal to minus, you can check your books, and if you have your books, tell me where this is. And then it's A sub P, and then it's crossed into the actual H field, right? Folks? Y'all with me on this? You can look in your book. Remember the cross product operation here. Since this is in the Y direction, it's minus 8 or 120 pi times AY crossed into the H field, and the H field is right here, so it's crossed into Z, correct? So it's Z crossed Y, and that means it would be, with that minus sign, it's going to give me a minus E right here of 120, or of 1200 pi, right? That's minus 3.77 times 10 to the 3rd. Do y'all follow me on this, class? Everybody got me on this particular thing? Give me 1 second. All right, now, it wasn't meant to be hard, but that's what the result will be. The frequency itself, you can get by, again, by beta here, it's lossless. 30 has to be equal to omega over c. Therefore, omega is c times 30. And if omega is c times 30, the frequency would be c times 30 divided by 2 pi. Are we clear on that, class? Everybody? I got to make sure. All right. So that takes care of this. This is the equation you would use. Next part for this propagational stuff, I put it down here. When you're talking about gamma, it's j omega mu times sigma plus j omega epsilon. And this is what you're going to get. And these are straightforward calculations. You just have to use the right frequency. Remember, omega is 2 pi f. And then for eta, it's j omega mu over sigma plus j omega epsilon. And this is what you're going to get. That's magnitude and that's phase in degrees right there. And let me pull it in. Try to pull it in. Come on. If I can't pull it, I can't pull it. Oh, there we go. So that's what it is. Now I'm going to save this. And I'm going to email everybody. And you should be getting this in a second. All right.
Dr. Baginski?
Yeah.
I think I know where a lot of people got confused with the propagation constant. And in homework 1,
hold on, let me get it up. Here's homework 1. For this part?
Yeah, I think that, I mean, I can't speak for other people, but for me, that's what I base it off of. And I guess now I know that, but that's kind of where I got confused.
That was something that got typed there, I think, in the lecture. I think I went through this several times about how to always find the direction of propagation from the coefficient of beta.
Mm-hmm.
Y'all remember that? That's what you look at. Orientation of the E field is X, but it's propagating in the plus Z. This one would be propagating in the plus Y. This would be propagating in the minus Z, right? Right. I'll give you one more just to ask you this. If you had something like this, E is equal to, say, 20 times EXP to the minus J quantity 2X plus, or 2X minus 3Y, and make it in the AZ direction. Now tell me from this one, what is the direction of propagation? I'll tell you 2 ways to do it. Take a look at that. This is a little more difficult. Just think about this. What does this term right here really imply? We were just talking about this. Isn't that like an X prime vector? It's neither in the X or Y direction, is it? Mm-hmm. It is as components of both, correct, class? And really what this is a beta of sorts, and it's going in an X prime direction. Now I'll show you how Whitworth's book says to get the direction of propagation. I want you to listen carefully. And this is, you can do it this way. This is overkill, but I'm going to show it to you. And I'm going to show it to you here so it'll stay in your homework, all right? Now, can everybody see what I'm writing here? Right? This is a fundamental question. It's actually a homework problem, has something like this. The direction of propagation you get by this, let me do it this way. So A sub P would be equal to, now you all know power flow is E cross H, right? You all with me? So if you take E times H, now you've got the power, magnitude and direction. Do you all agree with me? Right, class? That's power flow. If you take that and then you divide it by divide this by the quantity magnitude of E times times H. That's a cross product, but now I'm taking the magnitude of that. Oh, I'm sorry. I'm trying to get E cross H up top, but this is still correct right here. I want to show you something. Let me shut this down. I'll shut my emails off because here what'll happen is this. E cross H gives me the power flow in magnitude and direction. When I divide it by the magnitude, I just get the direction of propagation. Can you all follow me on that, class? All right. Now, if you're going to do this, because this is a fundamental question, if I wanted the H field from this, what would it be? Trying to do it right here. Well, what would the H field be? H is equal to 1. Let's say it's an air, all right? H is equal to 1 over eta, right? Right? And then it's unit vector in. That's not going to get me what I want. That's the definition, but to get the H field, let me just show you something. When I have the 2x plus 3y, let me go over here for a second. I'm going to get my camera on. I'll show you. I forgot what problem this is in the book, but it is in the book. All right, hold on. I've been having trouble with this camera. I'll try it again. All right, this one worked. I don't know why it does it. I think it's because it was developed with Windows 8 and I'm using Windows 10. All right, so getting back to this, I had an E field equal to, was it 20 E to the minus J, and was it 2X? Was it minus 3Y? Just tell me.
Yes.
And then it was in the AZ direction, right?
Mm-hmm.
All right, now what this is 2X minus 3Y. This E to the minus J quantity 2X minus 3Y really looks like E to the minus J some effective beta, and then it's in some, I'll call it an X prime direction. It's neither X nor Y. Now, first, if you look at 2X plus minus 3Y, just based on this, if you take a look at this, if I have 2X go 2 this way, 1, 2, and minus 3Y, this would be the vector 2X minus 3Y, right? Are you with me?
Mm-hmm.
Here, what I can say, I'm putting this, it's really, it's not really that's not proper. What I should do is say that this is 2ax minus 3ay. And I'm going to use the x and y. Well, that's a unit vector in the direction of propagation. The way I told you to get a unit vector in the direction of propagation last time was involving sines and cosines. Well, this itself has a magnitude, and it would be the square root of 2 squared is 4, 3 squared is 9, or square root of 13 would be a magnitude, correct? And then in terms of the portion of that that's in the x direction right here, if you think about 2x minus 3y, it would be, let's see, if this is 3, this is 2, and this is the angle theta. Let me try to draw this down here a little bit, because I think I'm going to run out of room. Square root of 13 is beta. And so this angle theta would be equal to tan minus 1 of 3 over 2. And this would be 13 times cosine of theta ax minus sine of theta ay. And this would be the actual unit vector in the direction of propagation. I mean, I should say it this way. AP would be equal to cosine theta ax minus sine theta ay. I'll finish this so you can see it. Let me get that angle for you. I want to do this. So I have just put theta equal to a tan of 3/2. So that's 56 degrees. And then my unit vector, AP, would actually be equal to I better do it this way. I'll just get the cosine by itself, cosine of theta. So what that does, and I should say this, what that tells me is a unit vector, this unit vector in the direction of propagation, I got to say this, and I'm going to try to make sense of this to you, because see, in Dr. Wentworth's book, when he talks about propagating field quantities, he does this, and I'm going to explain something. In his book, what he does generally is he has everything like the E field given as some E naught, e to the minus j beta, single direction, like x and then a y, something like that. Now, in the real world, this is how we dictate this. We say E in general is equal to some magnitude, E naught. That's the truth. Then we'll have e to the minus j. Now beta becomes a vector, and usually that they actually put k here. K is like beta, only k is a wave number, and it's like beta with a vector direction, right, in the direction of propagation. Can everybody follow me on that? And then that's dotted in right here with something that would be a vector r, and that's the way it's propagating, but this is the way the vector r is manifest. Instead of having just x or just y or whatever like this, it'll basically have like x times the cosine of the angle theta incident, and then it will be times ax plus y times the sine of theta incident ay. So this will be a second vector. Now the dot product of these two vectors will just be like 2x minus 3y. Does that make sense to everybody? That's this portion up here I try to show you. But that 2x minus 3y is really equal to some k vector times some r vector. The k vector is going to be the actual wave number equivalent to beta with the components in each direction. So it would be like cosine theta ax minus sine theta ay times 13. This would be the actual vector form of this. If this seems a little too far-fetched, just try to appreciate. I'm showing you things that Dr. Wentworth's book doesn't cover directly, but he mentions it in one of the problems. Now let me get back to the actual thing I was saying to you. The vector of propagation is when you do this, see how I just took the coefficient of x and put it an ax there, the coefficient of y and put in ay, and I drew a vector like this, right? The magnitude of this vector is the square root of 2 squared plus 3 squared. That would be the magnitude of beta, the real beta. The actual direction that this wave is traveling would be in this direction, all right? And this right here is really equal to that k vector, the wave number dotted into r, and r is going to be a portion of it and in the x direction, portion of it in the y direction, portion of it in z. Now this always, and I got to tell you this, the coefficients of the x, y, and z, the squares of those coefficients will always be 1. The actual wave number's magnitude is wrapped up in there. So I'll get back to you on this one. Now to get h out of this. The h field itself, you get, because we have the vector, we have the direction of propagation, which is this. And I got it by doing this. I had 2 and 3, so I could figure out a unit vector of propagation down here. Y'all follow me on this? I'm going to do another problem because I don't think I'm covering this quite as well as I should. But I'm going to get a vector direction, the direction of propagation. And then once I have that, and my AP is this, and actually for this problem, you can write this down. AP is given as, and I have to get my other thing, 0.555x or 0.555 AX, pardon me. And then it's minus 0.832B. I mean, AY, pardon me. So that's the direction, that's the unit vector in the direction of propagation. And it means that H would be equal to 1/2. I'm sorry.
You're supposed to be seeing this, what you're writing.
Yeah, that's my bad. Here's what I'm going to say. This is the unit vector in the direction of propagation. And I found the angle, right? And then I see that it's in the plus AX direction minus AY. Do y'all follow me on that part, class? You may not like it, but I'm doing my best because he doesn't cover this directly in his book. Once I have that, I get H, and I use the formula in the book because this is a plane wave. I take 1 over eta, assuming free space. Then I take this unit vector right here. Then I cross it into the E field. My E field actually was 20e to the minus j, we're going to be doing this today, by the way, 2x minus 3y in the AZ direction. Let me explain something. AP, the unit vector, has x and y components, right? Can you all see that? When you do this cross product, you put that here into AZ, you're going to have an H field that's going to have, well, if you have x cross z, right, you're going to get minus y. And then if you have z crossed, I'm sorry, if you have y cross z, you get plus x, but there's a minus sign there. So you're going to get another quantity with a positive sign, but it'll have an x component. Follow me on that, class? Now, this is a more complicated cross product, but this will become clear to you, I hope, in today's lecture. That's how you would always get the unit vector in the direction of propagation, by finding the magnitude of this. You can just put 2ax plus 3ay. The magnitude of that is square root of 13. And you've got to find the actual vector direction associated with this wave propagating. Now, I got to tell you one other thing, too, when you're doing this that's not in the book. You see how I put a minus sign there? That minus sign tells me that this vector right here, this information, is in fact the direction of propagation.
Can you
If that
pull
was
your
a,
pad down a little bit?
yeah, I'm sorry about that. What that minus sign does is tell me that this information here will be associated with the actual vector of propagation. When I replace x here by ax and y by ay, this will be a vector direction that's propagating. And now I have to find the unit vector. So I square both terms to find the magnitude, and then I divide that magnitude into the actual values 2 and 3, and I end up getting these coefficients, whatever. I find the cosine here and the sine here, but it's the portion going in the x and then the y direction. Does that make sense? If it doesn't make complete sense, hopefully today it will in the lecture. I'm going to do my best. All right. Any other questions? Now, this stuff, I'm going to tell you where it's in the book, and I want to go through this, and I want to tell you this much. Some of this is a little confusing, but it's important you see this. This is called oblique incidence. We've done normal incidence, right? So when you have reflection and transmission of oblique incidence, here's what you really have. You have an electromagnetic field. This is on page 360. You've got an electromagnetic field coming in and striking an interface between media 1 and media 2, hitting it and reflecting off, and some is transmitted. Probably on page 361, there's a better picture of this right here. You all have your books, by the way? If you see this picture, you have E, an incident reflected wave, and a transmitted. Now, I gave you some homework on this, didn't I? All right. If you didn't do it because you didn't understand it, I hope to clear that up, but you should always try it. Now, if the electric field is coming out of the paper, do you see how it has like a little, it just shows a circle with a dot in it? The electric field is perpendicular to the page. It's coming out. It's like this, coming out. And it's propagating into this interface. Some is reflected, some is transmitted. The orientation of the E field never changes. It's sticking out. It always will be. Now, the H field, if you look, remember, down here, E crossed H is the direction of propagation. Use your right hand to see that. E field coming out of the paper, take it with your index finger, cross it into the H field, and that thumb should point in the direction of propagation. That's how you get the direction of the H field, if you know the direction of propagation. Can you all see that? When it hits, some is reflected. You'll notice the E field is still sticking out. That means the H field has to be in a direction such that when it's crossed, when the E crossed H happens, your thumb points in the direction of propagation. I'm going to tell you this right now. It can be proved in a second. But the angle of reflection is always the angle of incidence. How many of you have played billiards at all? Pool? Have you all played pool or what is it, snooker? Any kind of game like that? Well, whenever the ball goes into the bumper, unless you do something funny with English, it comes off on that same angle, right? you know that's the sort of, it's the rule of, they call it the rule of bumpers if you're playing snooker, to make a shot. You know that to be true, so you can actually do some calculations and figure out where to hit the bumper in order to hit the first ball and hit 2 rails and have another if you play snooker. If you don't worry about it. Now, here I'm going to just mention, I'm going to write this down, but I got to make one note here. This is the z-axis. Can everybody see that? And this is the x-axis up. Y is out. That means the E field is polarized in the Y direction. I'm gonna just keep, if you look in your book, you're gonna see I'm following this more or less, but I'm gonna show you how this stuff works. Put it right there. Put it right there. So if I take a look at that and I take a look at the incident E field, and keep in mind, I'm talking about this field right here. This is the incident, it's the incoming field. Can you all see that? The wave's moving there. When I talk about that, E incident, that's going to have some value, and I'll use his notation, E0 incident. Then it's got to have an exponential term, e to the minus j, and Dr. Wentworth does not use a vector sense here. I wish he would, but he just puts it as beta, calls it beta 1 times z prime, and he puts it in the AY direction. Now, the key thing is what z prime is, and he says that z prime is going to be like this axis right here. I hope you can see it. It's this axis. Can you all see this right here? He's saying this would be the direction. Now, if you could project it, I'm going to do that next.
You need to shift it to the left a little bit. We didn't see that.
All right, this is z prime. It's coming in this direction. It's right on that axis. All right, now it has a projection on the z-axis and a projection on the y-axis. And he shows that right here in the next page. I'm going to develop it a little better. He says if this is, if it's propagating this way, oh boy, I don't like that. That's going to confuse you. Let me see if I can do justice to this. So bear with me. This is medium 1, medium 2. This is how the wave is propagating, all right? Now, I have some distance z here, and there's some distance x here that's covered over this, and I'll call it, he calls it z prime, doesn't he? Right? Take a look, that's his argument of beta, isn't it? Z prime. Now follow me on this. The angle that this thing's coming in is measured here. It's always measured to the normal. And that's like, if you take a look at this, this would be the incident angle right here. Can you all see that right there? It's always measured with respect to the normal. So the wave makes this angle with respect to the normal. Because of opposite interior angles, that means this is the same angle, doesn't it, class? Now please watch this and it'll make sense. When I look at z prime, I can say z prime is equal to z. This is going to be a right triangle. And if you look at this, if I take a cosine of this angle, it would be the length from here to here. So I could say it's equal to z times the cosine of the incident angle. All right. And then here's x, right? Now, if I take the sine, just look, that's theta incident, the sine of this, if I take the sine of this angle times this, I would get this distance. So if I take that plus x times the sine of theta incident, I would in fact get z prime. This is not going to be real apparent until you prove it to yourself, but just think about this. You all see if that's z, then z times the cosine of this angle is this distance, isn't it, class? You agree with me? I mean, you know how the cosine does. It takes what? It takes the projection of the hypotenuse onto the actual axis that's the nearest the angle, correct? Now, what does the sine do? If I have this, this is equal to, this is x. Well, if I take the sine of x, that's this over, that's the hypotenuse now. It's that over this, right? Correct, class? And I hope you can see this, but this angle is this angle right here, isn't it? Right? You can see that, can't you, class? Take a look at that. I mean, just let them both go down to 0. You can see those angles follow each other, or if they open up, they both open up the same way. Y'all see this? Can you all see how that angle is that angle? Just to show of hands, something that indicates you understand.
Right, so, okay, keep your pen where it is right now. That angle is the same as the two other angles, right?
The same as this is this. And you've had geometry, right? You've had to do this kind of stuff, remember? Yeah, sure. And just the way you do it is let these angles flare and see they both track each other. Let them go to 0. Don't they all go to 0? And let them go to 90. They all track each other. That's how you can see that they're the same. Now, the truth is, this is going to be absolutely true, and Wentworth has it somewhere in here. Where does he do that? I get, if you see this explicitly in yours, and I don't mind, let me know, but you see how the argument there now becomes x sine theta right here, x sine theta. Hold on. X sine theta plus z cosine theta in 6118. Can you all see that if you have your books? So what he's doing now is he's using this z prime for his z. He's basically adjusting it. This is the actual, this is the thing that indicates the direction of propagation. And I might add, if you want a unit vector in the direction of propagation, now listen to me carefully. Here he already had beta times just z prime, right? Correct, class? So what this is, you can say, is the unit vector in the direction of propagation will just be the cosine term, cosine of theta incidence in the a z direction, plus the sine of theta incidence in the a x direction. And that's how you get a unit vector in the direction of propagation. I'm going to tell you, you're not going to like this at first, because you can see one thing that happens just by observing this. See, he breaks out beta and he breaks out sine theta. He breaks out beta and cosine theta. In the real world, you wouldn't have that. You would have -2, like e to the minus j, 2x minus 3y, like I put there. Follow me? You all see that? So you would have to calculate beta like I did, and then you would have to calculate the unit vector in the direction of propagation like I did in order to write this form of an equation when you break them both out. Yes, sir. Somebody
So would it be like, instead of 2x plus 3y or whatever it was, would it be z plus x?
Well, this is x and z. I mean, sorry, yeah, this is x and z. I had x and y just because I arbitrarily chose those coordinates. But let me go on further with this, all right? Now, that's the first thing you have to see, how this vector is now being used as the directional vector. It does vary in x and y, but they have a coefficient. And this is a point on this axis. It'll take you a little time to appreciate it. You're just going to have to go with me on this one. And next, y'all see that that's the E field, right? Let's work with me there. Y'all give me that this is a vector, this is the vector, the unit vector in the direction of propagation would be, 1 second. If that's the E field incident, then the H field incident would be equal to 1 over eta, unit vector in the direction of propagation crossed into the E field. Y'all agree with that? Right? All right, let's do this one. I won't make you do them all. So the incident H field would be 1 over eta, whatever that is. Unit vector in the direction of propagation is this. So it would be cosine of theta incident AZ plus sine of theta incident AX, and it's crossed into E. Well, E is simply E naught incident, E to the minus J beta 1 Z prime, and I'm going to leave it as just beta 1. And here I'm just going to leave it as Z prime because it makes no sense to write this right here because we're going to be rewriting it. the thing I have to do is capture the vector sense, and it's in the AY direction. Correct, class? Work with me through this one. I'm not going to do them all, but you have to see how to get H if this is the incident E field. So I found the unit vector in the direction of propagation from the exponential argument, right? And now what I'm going to do is this. I'm going to say H incident is equal to, bear with me on this. You agree that eta is just a scalar if it's going to be in a lossless media? We're going to do this in a lossless media. It's too much trouble in a lossy media. Now, epsilon naught's a scalar, so I'm going to take the scalars out in front. So I'm going to have E naught incident over eta. Now, take note of this. I have e to the minus j beta z prime by itself, so I'll put e to the minus j beta 1. And you can put this in here if you want, right here, but it makes no sense. It just adds more work. Put z prime there. Now I have az crossed ay. What is that? Az crossed ay is, people?
Negative x.
AX.
Minus ax, right? Minus ax, and it's times what? Cosine of theta incident, right? You all agree with that? Now go to the next one. It's plus sine theta. Then we have ax crossed ay is?
Az.
Right. So it's plus az times sine of theta incident. And that would be the H field. Now appreciate the fact that this is, I appreciate the fact that this is tedious. All right. I usually do this on a board in class, and I write the fundamental equations. Then I show you the things you need to know, like the triangle and stuff like that. And then I go through it myself. I don't make everybody write it out. But that gives us this H field right here. Look at what we just did, and you see that there's a minus sense to the cosine of the incident AX, and a plus sense with the sine of theta AZ, right? Can you all see that? Now I want you to look here. E field's out of the paper, right here, right? But what about the H field? If you took projections of this, you see it's got a positive Z projection, but it has a negative X projection, doesn't it? Can you all see that H field? Take it and turn it into components. Positive Z, negative X. And that's in fact what you see, negative X, positive Z. Okay? Guys, you with me?
So in your, on the notepad you had, is z prime technically your propagation constant?
That is equivalent to the direction of propagation, like X or Z. If you look at this here, and I know this is going to take some time, but if you look at this, right? Suppose the angle is 0. I just want you to know that. If the angle is 0, if this angle right here is 0, then it's coming straight into the page, isn't it, class? If it's coming straight into the page, what does this become? Well, it's z cosine of 0. Cosine of 0 is 1, isn't it? Plus x sine of 0. Sine of 0 is 0. So it becomes just z, right? Now, do the other extreme. What happens if it's coming in at 90 degrees? It's basically coming in parallel. Well, at 90 degrees, the cosine of 90 is 0, and the sine of 90 is 1. So now you just have x. So that z prime is your vector. It is a measurement. It's something you're taking a measurement of how fast this varies versus that vector or that axis. And really the way I think is best to explain this, it's like taking an axis, trying to understand this. Suppose you have a grid, an XY grid like this. And now when we say Z prime, we're literally tilting these axes, and this becomes like our Z axis. It's called Z prime. That's the way you think about this. It's a tilted coordinate system, but it will take some time to get used to, because you're not like, you don't see vector axes in terms of two of the actual quantities involved in mapping points usually, but it is here. So just appreciate that. Anyway, that's H incident. Now, when I keep going on this, and I'm trying to manage time here, when I get the reflected fields here, can you all see them in your book? 6.121. I want you to just hang on now. If you're a little If this is too abstract, it'll get real in a second. Now, when we talk about the reflected fields, we're talking about this field, right? Propagating that way. Well, if this is Z prime, what happens? It's going to be similar to this, right? Only now we're going to have a positive X direction, but a negative Z. Do you all see that? It's propagating the minus Z direction if it's reflected, right? It goes in, bounces off, correct? How many see that right there? Its sense has got to be positive X, but it's negative Z. So now when I talk about the reflected wave, I've never had to do this using a tablet, using an overhead like this, and it's a different type of problem, I'll tell you. I'm not used to managing things on one sheet of paper. But I'll try. All right, work with me here. Now, when we do this, I'm going to say the reflected, first I'm going to give you a direction, vector in the direction of propagation for the reflected wave. This would be for the reflected wave, and this is a unit vector. It will be minus the cosine of theta incident AZ plus the sine of theta incident AX. I can prove that to you, but if you look here, you can see if this is the vector it's propagating in terms of the Z direction, it would be the cosine of theta reflected times AZ and be minus that, and it would be plus the sine of theta reflected AX. It's just the same as in magnitude as the incident, the unit vector in the direction of propagation for the incident wave, but the Z term has a negative sign on it. You all see that? Okay. Sorry for the messiness. Now, I need that because the reflected E field, by the way, I'll put this here, Z prime reflected would be equal to, using the same logic, it would have actually minus Z cosine of theta incident plus X sine of theta incident. Reflected, pardon me, reflected. And something I'm going to say right here, the reflected angle is the incident angle. That's always true. It never changes. I got to say something else too. We're assuming that this boundary is perfectly planar. When you get boundaries that have surface defects, this doesn't happen. But we're talking about a boundary between two plane layers, all right? Alan, that yawn is exactly how I feel, but I'm fighting it. Now, work with me on this. You all agree that that's a unit vector in the direction of propagation the other way? And this would be my Z prime for the reflected, not the incident. That's my new axis, right, that I'm moving on. So when I write the E field, and you always start with the E field for these things, and I hope I said this at the beginning, but this is called the TE mode of propagation. It's transverse electric. All right, bear with me. Now this E field will be some E naught reflected. I don't know the value of that. I just know it's going to have some value, right? Now I put the E to the minus J beta 1, and then I put my Z prime reflected here. That's this. I'm just going to put Z reflected prime. In the book, he puts in the sine and the cosine for the reflected. I'm going to just show you where it is. You don't have to write this down if you don't want, but I have to one time. You see what the reflected field's here? Remember, he's got the positive X, but the minus Z sense right there. Can you see it in 6.121? Take a look in your book. Okay. That's what this is right here. It's minus J beta and then this. Well, that means the minus times minus will give me a plus value in the end, but I'm just leaving it as that. And this is in the AY direction, right? Correct, class? Now, how do I get the H field, anybody?
1 over eta
Exactly.
times
Yeah,
the propagation.
you're absolutely right. The H field itself would be gotten as 1 over eta, unit vector and propagation, and this is the reflected now, crossed into the E field reflected. I can put that as ER. When I do this, this would be the reflected field. I find that H reflected here would be 1 over eta. This is a unit vector that would be minus cosine theta incident AZ plus sine theta incident AX crossed into E naught R e to the minus j beta 1 ZR prime AY. You can all see that this gets a little, there's a lot of redundancy and it's a little nerve-wracking, but you have to do it one time to appreciate it. Now, when I have that, what does H reflected actually become? Now, if you're writing, let me know when you're done so I can go ahead and keep going here. With me on this? All right, I want to bring out the constants. You see how I have just E naught reflected? I can pull that out in front, and then I have eta. So I have E naught reflected, and I have eta. Next, I can bring this e to the minus j beta 1 R z prime here reflected, because it's a simple scalar value. There's no, I mean, it has no vector sense, right? I can pull that out in front. It's not exactly a scalar, but it's got a real and imaginary part, but it's not a vector. E to the minus j beta 1 times z prime right there, reflected. And now I've got to do this business. I've got z crossed ay. Az crossed ay is?
Negative ax.
We're at the negative positive, right? So I have now the cosine of theta incident, all right, ax. And what happens here? Ax crossed ay is?
Az.
All right, and then I have plus sine of theta incident az, right? And that's it. And that's what he shows you. If you're writing this along with me, that's what he shows you right here in 6.121. But he includes the actual vectors right there. And you'll notice the sense, the polarization, it has both positive x and positive z. Can you all see that? You all see what I'm talking about right there? Now, if you look at that for a second, and you look at this waveform, I want you to take a look right here. This is on page 361, but you can see one thing that's really interesting. Now, if the E field is out of the paper and it's propagating this way, then E crossed H, take your right hand, put your index finger in the direction of polarization of the E field, then cross it into the H field. You see your thumb points in this direction. Try it. You all with me? This is how you always, in a plane wave, you always get the propagation direction by taking E crossed H. Your thumb is perpendicular to both vectors and pointing in the direction of propagation if you use your right hand for the right hand rule. Finally, when I get the transmitted field, I'm going to talk my way through this one because I frankly am getting tired of this. When you look at this, again, the tangent, this is for the transmitted component of the E field. You don't know the value, but you know it's got some E naught transmit. That's a coefficient, right? Can you all see this okay? You got your books, right? This is, how many have a book here? And you can look at, Alan, you don't have one? Yeah. There's somebody by iPhone. All right. If you don't have a book, please get a book. I mean, you should have it though, because Wentworth used this for EMAG 1, didn't he? Or I mean, Wentworth and Riggs or Adal or whoever you had for EMAG should have used this book for EMAG 1. Didn't y'all have this book for EMAG 1?
Yes.
Okay, if you had it, then this is second. I mean, you've got this book, but this equation right here is the same exact equation as our first incident field equation with one exception. All right, you see how it's beta 2 and theta transmitted. Beta 2, theta transmitted, and eta 2. And what I mean to say by that is this field here in the transmitted portion of this, now this is in, come on, this is on page 361. It's talking about the transmitted field. The E field's still perpendicular. E cross H is the direction of propagation. It's still moving this way. The only thing different is now the unit vector in the direction of propagation is going to change. That's A transmitted. And it will give me different orientations, but the general form right here will be the same. Now, I hope y'all can see this. Y'all see this right here? So now we go about doing business in calculating the reflection and transmission coefficients. This is so much easier with a board, at least for me. And I will not use PowerPoints for this. I'll refer to the book, but I just think it numbs students' minds. All right. Do you remember what we did when we calculated the reflection coefficient and transmission coefficient for just normal incidents? Anyone? What did we do? There was one key thing I'm looking for from anyone.
Gamma.
We did one thing. We set the tangent component of the E field on both sides of the media equal to each other, right? E tan 1 was E tan 2. And we set the tangent H field on either side of the media equal to each other. How many remember that? E tan 1 is E tan 2. H tan 1 is H tan 2. Now, when I talk about the tangent component of the E field from the incident and the reflected wave, I want you to notice this. Oops. Here, you know, when they talk about tangent, it's tangent to this border right here that's what? It's 2D. It's in the XY plane. It's like a big flat piece of paper sticking out of this. Well, the tangent component is the E field. You all see that? The H field has a portion that's tangent, but generally speaking, the H field has a component that's perpendicular in the Z direction. So when I take a look at this and I put E tan 1 equal to E tan 2, and I put E tan 1 equal to E tan 2, what I'm really doing is saying I'm going to put at the boundary, and at boundary, you notice that Z equals 0, right? We made sure that the boundary was put at Z equals 0. So if it's at 0, the reason that's nice is that, look, when it's at Z equals 0, this term goes away, right? The Z cosine theta incident goes away, doesn't it? There's Z 0, correct? So I'm going to do it right here. I'm going to take the E tan 1 is E tan 2. Well, the tangent field would be the incident field plus the reflected field at Z equals 0. So it would be, this would be the first equation. It would be E naught incident times E to the minus J beta 1. And then it would be X sine theta incident, AY. But I don't need to put AY on there because it's all AY. Then it would be plus E naught reflected, E to the minus J beta 1 X sine theta. And you can call it theta reflected if you want, but it doesn't matter. And that's equal to E naught transmitted, E to the minus J, and this would be beta 2 times X sine of theta transmitted. Now, the only thing I've done here is set the tangent component of the E field on either side of the boundary Z equals 0 equal to each other. And in Wentworth's book, it's equation 6.123. So his book does a little neater than me. Can you all see that in your book, guys? Everybody got that? Now, this is important. This has to be true at all points X, right? I want you to be careful to notice this. if this has to be true at all points, let's see if I can do this. Then what it means is that this coefficient, e to the minus j beta 1 x sine theta, has to be the same here, has to be the same value here. If it wasn't, then when you moved with x, these would not be equal. Can you see that? The argument of the exponentials on each one of these things has to be the same, or else the equation would fall apart. And so with that, then you can equate beta 1 x sine theta to beta 1 x sine theta reflected to beta 2 x sine theta transmitted. And what that says is the reflected and the incident angle must be the same. And then furthermore, when you take a look at this, it means that beta 1 x sine theta incident is beta 2 x sine theta transmitted, or really beta 1 sine theta incident is beta 2 sine theta transmitted. Do you follow me? And that is called Snell's law. How many have heard of Snell's law? Well, y'all had your physics here, right? How many remember Snell's law? You don't remember Snell? Okay. Well, here's how you get it. When you have, this is Snell's law, write this down. This is a biggie. If you go to an interview and you don't know this, they're going to think you're lying about your degree. It's like, you know how Ohm's law, if they ask you what Ohm's law is and you can't come up with it, they're going to look at you really funny. All right, it doesn't make sense to have an electrical engineering degree and not know what Ohm's law is. Well, it's the same thing if they ask you about Snell's law and you said to have taken electromagnetics. Snell's law says beta 1 times the sine of theta incident is equal to beta 2 times sine of theta transmitted. Now that's normally the way it is. And it also implied is the incident angle is the reflected angle. And remember, our angles are measured with respect to the normal. Remember that, not the parallel to the plane. Now, what that means is, if I want the transmitted angle, this is what we want. We usually know the incident angle. I can take beta 1 times sine of theta incident, and I divide it by beta 2, right? And then I take the inverse sine, and now I can get theta transmitted. I'm going to make this simple for you, so stay alert. Remember, I did this assuming it was lossless, right? So if it's lossless, beta in general is equal, for a lossless case, beta is omega times square root of mu epsilon, isn't it, class? Are you with me? How many remember or realize that beta is just omega square root of mu epsilon if it's lossless? Do you remember it? If you don't worry about it. It comes from just putting sigma equal to 0, and this will fall out of that equation if sigma's not there. Your propagation constant will become 0 plus j beta, and beta will be omega square root of mu epsilon. Now, if I put that in there for 1 and 2, then I get theta transmitted is equal to the sine minus 1 of, I can forget about the megas, and I get the square root of mu1 epsilon 1 over the square root of mu2 epsilon 2 times sine of theta incident. Now, that's true. And usually, for non-magnetic materials, theta transmitted is equal to the sine minus 1 of simply the square root of epsilon 1 over, or really epsilon relative 1 to epsilon relative 2 times the sine of theta incident. This is actually 6.127 in the book. It's called, he does call it Snell's law, and this is extremely important. So this is the transmitted angle based on the incident angle and known values of epsilon relative 1 and 2. And here I have to show you something that has to do with water.
What's that equation right there? Theta transmitted equals.
It's the inverse sine, sine minus 1, of square root of epsilon relative 1 over epsilon relative 2 times the sine of theta incident. As a matter of fact, I'm trying to see if he's got that there, and he doesn't. But this is for non-magnetic materials. It just means mu relative 1 is mu relative 2. Can you all read that right there, class? Can you all follow me? Now, I got to show you what that means with respect to water. And that's because I try to make sure that I can relate this to something you're very familiar with. You all look in water. I hope so, at least. Well, water has an epsilon relative of about 81. You can check that. That's rather large. Now, matter of fact, let me just do something for you. This is where you want, if you want to know where I'm getting some of this, in page 625 is the materials. You can see distilled water has epsilon relative of 81. This is on page 625, okay? Now, what does that mean? Well, in terms of the angle, well, suppose I have water here, all right? And that means I have epsilon relative equal 81, and I have air here. And epsilon relative of air is simply 1. And now I look at a wave coming in. So I'm going to have a wave coming in at, say, 45 degrees. And this is, I'm trying to just show you the wave coming this way. Can you all follow me? Now I want to see what angle it's going to make when it's transmitted. So I don't know. So I don't know what this is. In other words, the light will bend when it goes through there. So I can say that theta transmitted is equal to the sine minus 1 of the square root of, now it's going to be what? Epsilon relative 1 over epsilon relative 2, correct? Right? It's the square root of epsilon relative 1, or 81, over epsilon relative 2, or 1, right? Oh, sorry, I got this backwards. The transmitted angle would be equal to the sine minus 1 of square root of epsilon relative 1 over epsilon relative 2 times the sine of the incident angle. Now I'm going to put in the values. So the transmitted angle would be sine minus 1 of, and now this is 1/9, isn't it? 1 over 81 square root of that. Sine of 45 degrees is 1 over the square root of 2, isn't it? Right? So what is this? Well, I'll find out in 1 second, hopefully. So if I go ahead and say I want to know what that transmitted angle is, that's going to be a sine of 1 over 9 times square root of 2. And that in degrees is 4.5 degrees. Now I'll get what I'm after right here. So this means this actually angle here is 4.5 degrees, which is very small, right? This was 45 degrees. That's a wide angle. I mean, it's an obvious. 4.5 degrees is almost straight down, isn't it? And this is the thing about water. If you ever look into water at an angle, you can't assume that you're looking straight through that water in this direction. You're actually bent. What you're seeing is bent at an angle, both the waves flowing back at you and what you're shining down is being bent at a huge angle. It's being bent at 40, this only is 4.5 degrees. So if you've ever done this, and some of you have, Have you ever seen somebody shoot at a fish with a bow and arrow underwater? Anybody? Anybody know what bow hunting is? They shoot fish in water and stuff like this, or they try to spear them with. Well, the problem is this. Here's the guy's perceiving, and he's looking, and he sees a fish here. What looks here, but it's not there. If this is
You gotta
45,
push it up a little bit.
oh, I'm sorry. It's not there. If you're here and you're this guy and you're looking down this way, you perceive it to be there, but the actual thing is here. And so when you think the fish is there, you don't shoot right at the fish if you're shooting. You aim well below the fish. Has anybody ever heard of these things? That is because the light itself is being bent at that interface. And this is what Snell's law tells you. It tells you how much the light is being bent. And it's very important to understand that concept when you're making any kind of optical filters and things like that. It's Snell's law. And it also lets you do a few other things. But for now, you have to appreciate the fact that there's a huge amount of bending when you talk about epsilon relatives that have a big difference in them. And I'm trying to show you the obvious one, because most people are familiar with looking in water, and you can take a stick and just a straight stick and stick it in water and look like it breaks right at the surface and goes straight down. Just do it if you haven't done it. It'll help you get an appreciation for this. Now, my time is out, unfortunately, and I didn't get to the one thing I wanted to, so I'm going to mention it. And thank you for staying with me on this one. This is really the last section in the book. When I talk about TE polarization, I've gone through and I've showed you Snell's law, but one thing I didn't have time to do today is develop the reflection and transmission coefficients. This, in equation 6.133, is the transmission coefficient, or the reflection coefficient for the transverse electric field. This right here in the equation below it is the reflection coefficient, or is the transmission coefficient for the TE wave. Y'all follow me on that? Now this is oblique incidence, non-normal. And I'll get to some more things about this. Now, let me finish this thought. If you had a TM polarized wave, what that means is now the magnetic field would be out of the paper. It would be perpendicular to the plane that the wave is traveling in. You follow me on that, class? And a TM polarization, the E field itself would be in the plane of the paper, like this drawing shows you on page 366. And you can go through these equations, but on equation 6.14 here, this gives you, and I'm going to go through the difference, that gives you the reflection coefficient for the TM wave, and this on this equation on 6.142 gives you the transmission coefficient. The TM polarization is very important because there is a point, it's called Brewster's angle, where everything is transmitted into the second media. And I'm going to cover that next time. I'm going to give you some homework. I want you to do it for next time, okay? Do you have any questions now? Because we're basically done. This is my office hour. Anybody?
Can we do problem B from homework 4?
Yeah, absolutely. I'm glad I got a question about that. B from homework 4. Okay, let me do this. A TE wave having a magnitude of 10 volts and
The one under it.
this one, right?
There's a problem under it.
Oh, this one?
Yes.
This one? Okay. Yeah, we can do this one, no problem at all. Says a T wave having a magnitude of 6 volts is incidence from region 1 to 2. The wave is incident 60 degrees and region 1 is free space. Region 2 is a non-magnetic material with a relative permittivity of 9. If the incident field is that, determine the reflected and transmitted fields. Okay, here's how we're going to get this, if you want to stay with me on this. First thing I'm going to do is the wave is incident at 60 degrees, right? First thing I'm going to do is get the transmitted angle, all right? Does that make sense? Now I can write it here. Let me do it this way. We know that beta 1 sine theta incident is beta 2 sine theta transmitted, right? So if I look at what the actual angle of transmission, I'll call it theta transmitted is, that would be equal to sine or a sine. I can put a just means inverse sine. Now that's going to be and that's going to be for 1 second. It's non-magnetic, so it's really going to be SQRT of epsilon, sorry, divided by epsilon times the sine of 60 degrees. Y'all agree with that? That's the transmitted angle. So if I'm going to do that over here, so that means I have epsilon relative to 2 is 9, so that's going to be just 1/3, right? Times sine of 60. That's 1/2, isn't it, class? Right, sine of 60 is 1/2, correct? So I got not, I'll get this for you. So I got 9.594 degrees, correct, class? All right. Now, after that, wait, what do they want to get? They want E reflected, so we're going to get the reflection coefficient. This is something I didn't have time to put down, but I'll do it right here. And if you want, I'm going to go over here and use this. I like MathCAD for using this. Maybe I can get them both in the same window. I could do this with MATLAB too, but this is a little easier. So first I got to get the correct equation. Now bear with me on this one. And if you need to take a couple minute break to stand up and stretch your legs, go ahead. How many have another class right after this? Does anybody? If you don't, do you mind if I work this thing? I'll show you how to work it, but what I need is, and I'll do this, I'll put all the parameters right here. So for this one, E naught was equal to 6, right? The next thing, epsilon relative to, was 9, correct? Right? And then theta incident was 60 degrees, right? And what else? So we figured out what theta transmitted was right there, 9.594 degrees. Now the reflection coefficient, and I'm going to use this symbol. It looks like gamma, but not really. It's just capital T, and I'm going to call that the reflection coefficient. That's equal to this is really A to 2, but I'm going to use N2 times, and this is on page 364. Let me show you exactly what I'm doing. I'm going right on page 364, and I'm using this equation. You see it has N2 cosine theta incident minus N1 cosine theta transmitted. All right. So actually what I better do is put down what eta 1 and eta 2 are. I'll do it right here. So I know eta in general is equal to the square root of mu over epsilon, right? All right, so I know that eta 1 is really equal to eta naught, and I'm going to put it right here. Eta naught is just 120 times pi. Is everybody okay with that, class? That's what free space is. It's what air is. Now, eta 1 is eta naught. Eta 2, on the other hand, is square root of mu epsilon, but epsilon for that one is 9, correct? So I can say that eta 2 is square root of mu naught over epsilon naught, or 120 pi divided by square root of 9, or really it's going to be what? It's eta naught, right, divided by 3, isn't it? If you need a value, that would be it. Do you agree with that, class? It's the square root of mu over epsilon. That's all it is. Now, if you have that, now I'm going to come down here, and I've got to get, I know the incident angle, and I'll put it this way. Theta I was equal to 60 degrees, and 60 degrees is pi over 3 radians. Do y'all agree with that? 60 degrees. And I know the transmitted angle is right here. Now, I wanted to render it in terms of degrees, but normally if I got rid of that degree, and this is a nice thing about MathCAD, it'll give it to me in radians. See how it is in radians there? But you can leave it in degrees and it won't matter. If I like everything in degrees, I don't know what that is in terms of radians. I don't have a good idea. So I leave it in terms of degrees. That's another reason I like MathCAD. It allows me to see stuff. Now I put in the equation. If you look in your books, this is going to be cosine, right, of theta incident, right? And then it's going to be minus eta 1 times cosine of theta transmitted, right? Right? And then it takes these terms, just bear with me, guys. I'm not the best at this, I'm trying to highlight that. And I have to divide this, come on, by that, but instead of minus, this is a plus. Look at that equation, you're going to see this becomes a plus, right? Can you all see that? Grace, can you see that in the book? It's equation 6.133. I'm just taking the coefficient of E naught incident there. Can you see it? Now, this has a value of minus 0.711. That's the reflection coefficient. With me? That means the reflected field for that one is actually going to be that reflection coefficient times E naught. That's the magnitude of the reflected field. Follow me? Now, to get the actual e to the j business, I want to show you this. This is going to be the magnitude of the reflected field. But I'm going to come over here and I'm going to show you something. You see how you have this information right here? It's e to the minus j 1.814x plus j 1.047z, right? For the reflected field, I'm going to copy that if I can. And I'm going to put that right here so y'all can see it. The reflected field will have a magnitude of, what was it again? Minus 4.265. And then it's going to be this, but here's what changes. The z is going to have a negative because it's going in the negative direction. Do you follow me? The reflected field bangs in there and it's traveling, has a minus z aspect to it. Do you all see that?
Where'd you get the minus 4.265?
Right.
From
here.
multiplying the
Reflection coefficient times the incident field.
Okay.
Remember, reflection coefficient is that, and the incident field was 6, isn't it? Everybody? Brandon, can you see this okay? All right. This is about as good as I can do with what I got to work with right here. So I get this, and now I'm not quite done. It's still in the what? It's still going to be oriented in the AY direction, right? Or A sub Y. Correct, class? That would be the reflected field. How do I get the transmitted field? Take a guess. Well, I didn't get to it today, but I'm going to right now, and I appreciate everybody sticking around. To get the transmitted field, I come over here, and I see that the transmitted field is 2 ways I can do it. I can calculate this right here, right? Take a look. Or I can just add 1 to the reflection coefficient. I got the transmission coefficient. Now that's only true for the TE wave. It is not true for TM, and make sure you realize this. So when I go through to calculate the TE transmission coefficient, I just take the reflection coefficient plus 1, which makes my life a little bit easier. So I come over here and I say, I hope you bear with me. I come down here and I'm going to say now the magnitude of the transmitted field will just be 1 plus the reflection coefficient times E naught. And that's 1.735. Everybody all right with that? So, and I hope you're still recording. All right, good. So that comes over here. So now that's, what did I say? 1.735, right? But here's what I have to do. I have to get, for the exponential, I have to get the actual new vector. And here's what I mean by that. Remember how the unit vector has the cosine of theta transmitted AX plus the sine of theta transmitted AY? All right, and what I'm talking is, just bear with me. I'm going to here and I'm saying that, look. When I look at the equations, the transmitted field down here, can you see that they have X sine of theta transmitted plus Z cosine of theta transmitted? Right? So, and I need to calculate a new beta 2 as well. So the first thing I'm going to do is say that, well, let me go back here for a second before I confuse you. Now, this right here is something that we need to find the value of beta for, don't we? Correct, class? How do you find the value of beta right there?
Square them both and find the magnitude, right?
You're going to square the coefficient of X and square the coefficient of Z, add them both up and take the square root. Do you follow me? So I can put down here, this would be beta 1 though. So beta 1, I'll put it here just for everybody's sake, would be equal to the square root And then it's going to be 1.814, right? Squared plus 1.047 squared square root equal. I don't know if it'll let me do this. I'm going to see if I can. So that's kind of nice. Can you all see that? 2.09447. So that's what beta 1 is, okay? Now, how do I get frequency from that? Class? That's beta, right? Come on, how do I get frequency? What is beta? Isn't it omega divided by c for free space? How many remember that? You just did this, right? It's omega divided by the speed of light if it's in free space, and this is in free space. The first one is a wave incident from region 1 is free space. So that means I can say that the frequency, right? I'll do it right here. I can say that F would be equal to beta 1. Matter of fact, let me just put this 2.09447 there. It's beta 1, right, divided by, no, I'm sorry. It would be times C. Let me restate that. Beta times C divided by 2 pi. So it's this times 3. This, I don't know if that's times or not here. Times 3 times 10 to the 8th. I don't know if this is going to do it. Divided by 2 times pi. I'll see if this will allow me to calculate. I'm not sure it will. It did. So that's really 10 to the 8th, isn't it, class? About. Is that right? Is that what you guys get? I can do this over here. Just check it, all right? I'm wondering about that.
That's what I got.
Yeah, that's what I got. So it's 10 to the 8th is the frequency. Now, the reason you need that frequency is now you got to get beta 2, don't you? Right, class? How do you get beta 2?
Did you just do the beta 1 sine?
No, but this is beta in region 2. Beta. What is beta? Isn't it omega times the square root of mu epsilon, right? Let me write this down for you so you don't make a mistake. Look, this is an office hour, so.
So why can you use Snell's law here?
We're after beta, aren't we? We don't know what the transmitted angle is yet, do we? Or we actually.
Don't we?
Well, look, we've got the incident angle is 60, right? we have beta 1, right? We don't have.
You found the transmit the second angle is 9.9 or
Yeah.
5.9, right?
You're right. You could use Snell's law, but I'm going to tell you the way I like to always get beta, and let me do it with the doc cam. You're absolutely right. You could. What I'm going to do is this. Remember that gamma is alpha plus j beta. All right. Now that's equal to the square root of j omega mu over sigma plus j omega epsilon. We know that. If it's lossless, sigma is 0. That means gamma is equal to 0 plus j beta. And if sigma is 0, we have j omega times j omega. So we bring that outside, just j omega. Then it's the square root of mu over epsilon. That's really j times omega. The square root of mu over epsilon is c. And then it's times the square root of epsilon relative, mu relative here. Now I'm doing this rather quickly because I know we've been here for a while, but I'm trying to show you that omega over c is the thing that comes out front, and you just weigh it by the square root of epsilon relative, mu relative. If it's non-magnetic, you get rid of mu relative. Now in our region 2, this would be beta then, this and this. Beta in region 2 would be equal to omega over c times the square root of epsilon relative 2. Omega over c was what beta 1 was, isn't it? Right? All right, beta 1 was 2.09 something. Can you tell me exactly what it was?
2.09447.
All right, it's that times the square root of epsilon relative 2. Epsilon relative in region 2 was 9, right?
Mm-hmm.
So it's this times 3. Or beta in region 2, I'll do it right here. You can do it with me. Is just going to be the, let me do it here.
Do you want us to be seeing your computer right now, or?
I'm going to pull it over. No, I'm just doing the calculation myself.
Okay.
It's 2.09447 times 3, right? And that's 6.283. So beta 2 is just 6.283, right? Did you guys get this, by the way? I know I've been dragging on, right, everyone? All right, now if we got this, what does that mean your vector, I mean, what is z transmitted, that small z transmitted going to be? It's going to be z times the cosine of theta transmitted plus x times the sine of theta transmitted, right? Remember how we had that, that's that, like that z prime vector? Mm-hmm. Now we're in region 2. Well, what's this? Well, that's really z times the cosine of theta transmitted. Well, the cosine, now the transmission angle was what? It was, I'm looking, 9.594 degrees, right? Guys, are you with me?
Mm-hmm.
9.45. So it means what we do here is we take the cosine of 9.45, multiply it by z, and we take the sine of 9.45 and multiply it by x. That's like the coordinate z prime, and then our unit vector in the direction of transmission here would just be cosine of theta transmitted, a z plus sine of theta transmitted, ax. Okay? Are you with me? Okay. Now you asked about this, and I'm going through it, and I know this may not be the answer you're looking for, but I'm trying to do my.
So when I got a different beta 2 when I did the Snell's law way. So
well,
maybe
well, I mean, just do it with me right now, and we can. It has to be consistent. But I know that beta 1, right, times sine theta 1 is equal to beta 2 times sine theta 2, right? Oh, I'm sorry.
Yep.
This has to be true, right?
Yes.
If you wanted beta 2, it would be beta 1 over what? Or beta 1 times sine of theta incident over
Sine of theta transient.
right?
Yeah.
All right. Well, beta 1, the sine of 60 is 1/2, right? Then I have divide this by the sine of the transmitted angle. But we use this to actually calculate. What was the transmitted angle again? 9.594? That's degrees. Let me see what it comes down to. That's exactly the same thing. Yeah. It has to be. See right here? Beta over 2 sine of 9.594 degrees, 6.283. They're the same. All right. You may have be in radians or something. All right. You got to make sure you have the argument of sine is either degree or radians, but it has to be right. Okay, everyone? That's going to be the same. So that's beta 2. Now, after you have beta 2, then you can come back to this equation. And I'm just, if you, let me just see what else I wanted. So just listen. Y'all agree we can get the transmitted field fairly straightforward right now? Because we have beta 2, we have the cosine, so we can make adjustments to this exponential argument. It'll be in the AY direction. We can get we've got the frequency to get H. The H is actually specified on page 362, isn't it, class?
Hey, Dr. Baginski, I know what is wrong. You're saying sine of 60 is 1/2. It's really the 0.86 root 3 over 2.
That's cosine. Oh, wait a second. I think you are right. I'm sorry, you're all right. My bad. So that means our beta 2 is wrong in the beginning. Let me just get this right. This right here leads to a beta 2 of 2, or a beta 1 of 2.09447, right?
Mm-hmm.
Now, if that is the truth, if we want to get beta 2, I know that beta 2, I'm so sorry about that. Over here, if I want beta 2, beta 2 is equal to omega times square root of mu epsilon. That's equal to omega times square root of mu naught epsilon naught square root of mu relative epsilon relative in region 2. That's omega over c. That's what this is, omega over c. And this is a square root of, and we'll assume non-magnetic, so it's just square root of epsilon relative 2. Well, omega over c is the same thing as beta in region 1. Do you all agree with that? So that just is 2.09447. Now I have the square root of epsilon relative 2. Epsilon relative 2 is 9, so it's simply times 3. That will be beta 2 period. Do you agree with that? Now to get the angle, the incident angle or the transmitted angle. First, we'll get the incident angle, and we can get it, forget what's stated. If we look at the actual problem, it has this right here, right? Can you all see that right there? Now that's a vector, and I'm going to draw it for you. Let me get the camera on. Think of this as my interface in the region right here. And if you look at this, it's coming, oh goodness, I drew this wrong. This is Z, this is X. It's 1.814X. And then it goes minus 1.047 AZ, right? So technically, you're supposed to have e to the minus j beta quantity here, and it'd be cosine theta incident AZ plus sine theta incident AX, or I mean X, pardon me. Well, this vector would look like this. It would be it have a dimension this way of 1.814 and a dimension this way, trying to do this right, of 1 point, I got this wrong. It's actually going to be the opposite way. The X has a dimension of 1.84 this way. And Z is 1.47 this way, which means this angle, if I want that angle, what I'm actually getting is this angle right here. So that angle right there is going to be tan minus 1 of opposite, which is 1.814 over 1.047. Let me see what that is. I'll tell you if that's 60 degrees or not. It is 60. So it was right. It is 60 degrees. All right, and then that means if that is 60 degrees, then beta 2, we have beta 1, and I do beta 1 sine of theta incident, which is 60, is equal to beta 2 sine theta transmitted. If I divide that by sine theta transmitted, that would be beta 2. Let me just see what this is. So Let's see this. This, wait a second. This value of beta 2 is correct. What did we do? It was messed up. The transmitted angle, did we mess that up? I think we did. I think this is messed up right here. Our transmitted angle should be beta 1 over beta 2 times the sine of theta incident and then a sine of that. So that's what we messed up. I messed that up. So that means right here, theta transmitted, just bear with me and I'll leave you go. Theta transmitted should be equal to a sine, the inverse sine of beta 1 over beta 2 times the sine of theta incident, which is pi over 3. I'm going to have to get new values here. I got to put beta, this is beta 2. Beta 1.
I'm sorry, I have to go. Thank you, though.
I'm just finishing this problem because I started. I'm feeling bad. So the actual angle of transmission, let me put it in degrees. Come on. It's 16.779 degrees. My bad. I'm sorry it took this long. And then it will be consistent. Then you would take the cosine of that and the sine of that to get the coefficients of z and x for your transmission. All right.
Mm-hmm.
Do yourself a favor, work through this. Let me see if I can put some answers up for some of these, and I'll give you some more homework for next time. And I'm sorry it took so long. I didn't mean to make a mistake, but I guess I was a little fatigued. All right, guys. We'll see you next time. Thanks for hanging out for this long, but we need to do an office hour now and then.
Yep.
All right, guys. You take care.
Thank you.
Bye-bye.